Well, good morning, everyone. I hope that you had a nice break. I just put the scores for exam 2 up on Blackboard because I didn't want to ruin anybody's break. We'll talk about that in a minute. This is Chapter 6. Chapter 6 is yet more calculations, is quantitative aspects of chemistry. Basically, this is the chapter on stoichiometry. Now, we're going to try to approach stoichiometry so it's nice and simple and whatever. There are some topics that are in the chapter that we will go over because I want you to have a concept of what they are and we'll work problems. But they probably won't make it on the exam. Basically, we're talking about limiting reactants. So that'll be the section at the end of lecture today. Again, we'll work lots of problems, but we're not really going to have that type of problem. You'll probably understand that as we get to it. With exam 1, especially after the online makeup, most people did fairly well. They managed to have a fairly decent score, etc., etc. Now, exam 2 gets more quantitative than it was in exam 1. There were still some very good scores, mind you. High score was in the mid-90s, I think, maybe upper 90s, something like that. But there were some people that just didn't do quite so well. So there will be an extra credit that comes online on Wednesday. This will be 20 points, and it will be added directly to your exam 2 numbers plus score. You'll probably have either 1 or 2 attempts at this, that's it. But it's a chance to remedy if you didn't do quite as well on exam number 2. I was a little surprised, I didn't quite understand. Questions on exam 2 look very, very much like the sample exam we went over in class. Maybe so much that people thought they were taking the same exam without realizing that they were all different questions. Because a lot of people put down answers that were from the sample exam and not this. But so please pay attention to the exams. The purpose of the sample is to, again, not freak you out when you see what the real exam looks like, but they will be different, so remember that. In lab last time, if you can remember all the way that far back, we did some simple mole analysis stuff. This is just a cute little video of a flame test that's a little more interesting than simply dipping a wire.
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with barium ions burning a yellow, a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally potassium with the purple or lilac shade.
So it's kind of a really neat demonstration. What you do is you have a bunch of little Petri dishes lined up, a little wad of cotton in each one, alcohol, and of course you put in the appropriate salts. Get the room very dark and then throw something at it that's burning, and it kind of like goes up in a big floof. If you can get a very nice dark room, it's a real cute way to do that. You might wonder exactly why things burn in different colors. For example, strontium is red, and over here, copper is green, etc., etc. That's because, as we learned in Chapter 1, all of these elements have different electronic configuration. When you heat something up like this, what you're doing is taking an electron, usually even a core electron, something stupid, and you promote it to a real high energy level because you're heating it up so much. Well, it doesn't stay up there, it falls down. And as it falls down, it releases this energy as light. Because they all have different electronic configurations, the electrons that do this bouncing up and down are unique. And that's why every element with a different electron configuration will emit a different color. This is a very crude demonstration of a very powerful analytical technique that will allow you to take just micrograms of something and actually determine what the elements are using the same sort of technique here. All right, let's go ahead and talk a little bit about stoichiometry. Now, we've addressed stoichiometry many, many times. We've seen this thing where we take bromine, aluminum, and we make aluminum bromide. Again, here's our reaction arrow. We know that we can insert coefficients on both sides of the reaction so that we get the same numbers and types of atoms. For this, it looks like this. 2 aluminums, 3 bromines, 2 aluminum bromides. Now, as we write this equation, we're actually talking about atoms. Atoms of aluminum, atoms, or actually molecules of Br2, molecules or formula units of aluminum bromide. But as we said, we can also express this simply in terms of moles. If we look at this, we could say 2 moles of aluminum react with 3 moles of bromine, and 2 moles give 2 moles of aluminum bromide. So all we're doing is taking our balanced equation and we're describing it in molar terms. Well, these coefficients represent what we call the stoichiometry of the reaction. And what we're doing in this chapter is we're going to do calculations based on that stoichiometry. Let's say that we had ethanol reacting with oxygen to give carbon dioxide and water. Okay, nice simple reaction. Step 1, you want to look and make sure your equation is balanced. We have 2 carbons, we have 2 carbons, we have 4 oxygens, we have, let's see, how many oxygens? No, that's 6, 7. We have enough oxygens. It's balanced. The question is, based on this chemical equation, how many moles of CO2 will we get if we have 2.5 moles of ethanol? So that's a classic stoichiometry question in terms of moles. Here's our balanced equation. If we have 2.5 moles of ethanol, that's our given, how many moles of CO2 will we get? Now, we're going to approach solving these problems 2 ways. I told you that we could always use our algorithm, the given ratio find, in order to solve virtually everything you're going to do in 110. Virtually everything. So we're going to solve it this way first. But then we're also going to look at another method that's essentially identical, but I think it's easier. Just has to do with ratios. Let's start off with our classic. In this problem, we're given that we have 2.5 moles of ethanol. Now for a ratio, what we want to do is look at our balanced equation and simply write a stoichiometric ratio. The stoichiometric ratio here, we're looking at carbon dioxide and ethanol, right? If you look at this equation, every ethanol gives us 2 CO2s, doesn't it? That's all in the world we mean by stoichiometric ratio. 2 CO2s for every ethanol. And of course, we're trying to find CO2. All right, let's take this and construct our solution. Our given is simply our 2.5 moles of ethanol. To do our ratio, we look at the stoichiometry. We remember that moles of ethanol must be in our denominator. So our ratio is 2 CO2s for every ethanol. So we simply write our ratio like this. Moles of ethanol are going to cancel. And again, we're just left with moles of CO2. Our calculation is so simple I can do it in my head. 2.5 times 2, 5 moles of CO2. Now, our stoichiometric ratio here, 2 to 1. These are exact numbers, aren't they? It's not about 2 to 1. It's not approximately. It's exact. And because it's exact, we don't have to worry about these for significant figures. So we have two significant figures here and 2 in our answer. Any questions? Now see, that's really simple, isn't it? You can do this in your head. If we had 1 mole of ethanol, we would get 2 moles of CO2. If I told you in the problem we had 6 moles of ethanol, we would have 12 moles of CO2. That's all in the world stoichiometry is. Let's do this the other way that I was telling you about, and that is to set up 2 ratios. As we look at our problem, and as we look at our stoichiometry, we can write 2 ratios. A known ratio, that's the stoichiometry, and an unknown ratio. That's the question in our problem. Our known ratio here is simply going to be the relationship between ethanol and CO2. So we look at our balanced equation. We ask, what is the stoichiometric ratio? This obviously is simply 2 to 1. All right, so that's just our ratio. That's our stoichiometry. Now the unknown ratio comes from the problem. When you set up your unknown ratio, make sure it's set up the same way. CO2 on top, ethanol on the bottom, or flipped over, doesn't matter, as long as the 2 are the same. But our problem is asking us how many moles of ethanol, or how many moles of CO2 will we get for 2.5 moles of ethanol? Now, Mathematically, when we say how many, we can simply say X. X moles of CO2 for 2.5 moles of ethanol. Now, in terms of using your calculator and solving these problems quickly and easily, you can just look at this algebraically and say, okay, I'm going to cross multiply 2.5 times 2 divided by 1. That's my answer. So that's one reason it's easy. It's easy to set up and run through your calculator. If we went ahead and just did this stepwise, that is, multiply both sides by 2.5 moles of ethanol, we will get this, right? All I've done is move the ethanol over. Now look at this. Isn't this exactly the same as our standard algorithm? Here's our given, multiplied by our ratio, and our units are identical in our denominator. Once again, 2.5 times 2, 5 moles of CO2. So you simply look at your stoichiometry. You set up a known ratio. You look at your problem, and you set up an unknown ratio. Any questions? All right, calcium with HCl to give calcium chloride and hydrogen. We want to know how many moles of HCl we need to react with 3.25 moles of calcium. Now, instead of reactants and products, this problem is only reactants, isn't it? But still, we can do that. Step one, we want to think about our known ratio. Our known ratio is going to be the relationship between calcium and HCl. That's our known ratio. Our unknown ratio is going to be X moles of HCl, 3.25 moles of calcium. So, our known ratio, 2 moles of HCl for every mole of calcium. Straight from the equation, right? Our question here, how many moles of HCl, that's X, for 3.25 moles of calcium? Now, if you had your calculator out, you would just say, fine, I can cross multiply 3.25 times 2 divided by 1 and get my answer. If you like multiplying things out stepwise, 3.25, multiply both sides by that. This is our given, isn't it? This is our ratio. Our units match. Once again, 3.25 times 2 divided by 1, 6.5 moles of HCl. Any questions? All right, let's look at another one. This is the organic molecule ethane. It's reacting with oxygen to give CO2 and water. Now, the first thing you always do, of course, is to look and say, is this equation balanced? Is it? Absolutely not. Just right away, we have 2 carbons, we have 1. So take a second and balance it. We have 6 hydrogens here, so we're going to need at least 3 waters, right? That would give us 2 CO2s. But if we did that, we would have 3.5 moles of oxygen. Need 7 oxygens. Doesn't work. So we double everything. Going to have 2 of these guys, 6 waters, 4 CO2s, and 7 moles of oxygen. All right, so now take this and let's look at our problem. We want to know how many moles of molecular oxygen, that's O2, so that's going to be X, are going to give us 1.7 moles of CO2. So step 1, you want to write a ratio for molecular oxygen and CO2. That's your known. And then your unknown is simply going to be X moles of oxygen, 1.7 moles of CO2. Go ahead and set it up. Our stoichiometric ratio between oxygen and CO2 is going to be 7:4, isn't it? That's just from the balanced equation. Our unknown ratio is going to be X to 1.7. Now that makes sense, doesn't it? Our known, 7 moles of O2, 4 moles of CO2. Our unknown, X moles of O2, 1.7 moles of CO2. And on your calculator, you just plug in 1.7 times 7 divided by 4. This is the operation. Here's our given. Here's our ratio. 1.7 times 7 divided by 4. 2.975 exactly moles of oxygen. Now, we are dealing with 3 significant figures, right? We have to round this. Remember our rule? If it ends in exactly 5, what do? We round it even. Even. So this is 2.98. See, you got to use something you learned earlier. Yeah?
When you say round even, like you mean round up?
Well, no. If this was 875, I'm sorry, if this was 985, 9.85 and we're rounding. Hang on, I'm working on it.
Okay.
Oh, yeah, okay, 9.85. Instead of rounding up to 9, we would round down to even. It'd still be 9.8. You just want to make sure your answer always lines up even. But only in the case that it isn't exactly 5.
Oh.
All right, of course, there's a tutorial or two about molar stoichiometry. And this is going to use simply the ratio method that we've been talking about. So this up here is meant to remind you, we take our known ratio or unknown ratio and simply solve for our unknown. You could also do this using the given ratio method. Again, whatever works, works. Now we're trying to find sodium, hydrogen, carbonate. So that's our X. We are given moles of sodium carbonate. So when you write your stoichiometric ratio, what you want to do is simply get the ratio between sodium hydrogen carbonate and sodium carbonate. That ratio, very simply, 2 sodium hydrogen carbonates for every 1 sodium carbonate. So that's our known ratio. Our unknown, how many sodium hydrogen carbonates, that's X, for 0.8217 moles of carbonate. Sodium hydrogen carbonate to sodium carbonate. That's these two guys. Our ratio, our stoichiometry, our known ratio is 2 to 1. Okay? Our unknown ratio, our question, X moles of sodium hydrogen carbonate and 0.82 moles of carbonate. Again, all we would do is take 0.82, multiply by 2, divide by 1, and you get 0.164. Any questions? We'll do one more here, and I will hush, let you set up your ratios. Aren't you glad you didn't have to balance that equation? This is called chloroethane, again, an organic molecule, and of course chlorine. We're looking for the relationship between chlorine and chloroethane. Every 4 chloroethanes gives 2 chlorines. So you could write your ratio 4 to 2 or 2 to 1. Doesn't matter. And our unknown is going to be X over 0.9922. 4 to 2 is our known ratio. X to 0.99 is our unknown ratio. all in the world we have to do is take 0.99, multiply by 4, divide by 2, 1984. It's a very good year. Any questions?
I think it's like the only part that it's hard from this problem is to figure out the ratio, so it's always the coefficient that you look at, right?
Yep, just the relationship of the coefficients, 4 to 2, or you could just simplify it as 2 to 1. All right. Well, we've done all of these in terms of moles, right? But in the real world, in the lab, I don't tell you to go in there and weigh out a mole of something, do I? No. You weigh out so many grams. We're going to do stoichiometry problems now based on mass. We know that potassium chlorate, when you heat it up, gives us KCIO and oxygen. Remember, we saw that when we tortured our gummy bear. Here we want to know how many grams of potassium chlorate we need to give us 2.25 moles of oxygen atoms. Now, I did this on purpose. The previous problem we talked about molecular oxygen, right? That was O2. If I ever want you to do a calculation based on individual atoms, I will say the word oxygen atoms. Okay? Just to point this out. All right, what I want to do here is to start off our discussion of mass by doing it the long way. What we're going to do is solve and see how many moles of KClO3 we need. And then we're going to convert the number of moles into mass. Because we know that, what is it? Mass times molar mass is moles, right? Never forget that. Our known ratio here, for every 2 potassium chlorates, we get 6 oxygen atoms. We get 3 O2s, but again, for some bizarre reason, I asked for atoms, so let's leave it oxygen atoms. So that's our known ratio. Our unknown ratio is how many KClO3s for 2.25 moles of oxygen atoms. So, to get our moles, what do? 2.25 times 2 divided by 6. That's all. And we wind up with 0.75 moles of potassium chlorate. Okay, so we have 0.75 moles of potassium chlorate to give us 2.25 moles of oxygen atoms. Unfortunately, the problem wants to know a mass, doesn't it? But if we know how many moles and we know a molar mass, all we have to do is convert 0.75 moles into mass. Now, if this was an exam question, of course, I would give you the molar mass of potassium chlorate. If I didn't give it to you for some bizarre reason, you would just go to the periodic table and you would add it up. Easiest way is for me to push the button and tell you that it's 122.54 or so. So, if 1 mole is 122 grams, how many grams is 0.75 moles? All we have to do is take our given, which is the number of moles. Going to use our molar mass as a ratio. 122 grams per mole. Moles, of course, will cancel. And we're left here with 91.9 grams of potassium chlorate. Again, think of the mass logic here. If you had done this calculation and you needed 1 mole, it would be 122 grams, right? You only need 0.75 moles. So just multiply the two together and get your mass. Any questions? All right. Zinc sulfide, heated in the presence of oxygen to give us zinc oxide at SO2. If we have 25 grams of zinc sulfide, and we have all of the oxygen we ever need, that's called excess, how much zinc oxide will we make? Again, this is real life, isn't it? You don't go in and weigh out so many moles. You go in the lab and you weigh out 25 grams. If you have 25 grams of this stuff, how many grams of this are you going to get? Okay. If we knew how many moles of this we had, we would know exactly how many moles of this we'll get. So all we have to do is simply use our mole mass conversion stone. Our known ratio is going to be 1 zinc sulfide for every zinc oxide. 2 to 2, 1 to 1, same thing. Our unknown ratio is going to be 25 grams of zinc sulfide and X grams of zinc oxide. Start off this way. I tell you I have 1 mole of zinc sulfide for every mole of zinc oxide. But I'm smart enough now that I know that since everything here is in terms of mass, I can make life so much simpler for myself if I just say zinc sulfide at 97.46 grams. If we had 97.46 grams of zinc sulfide, that would be the same as 1 mole, wouldn't it? And if we had 81 grams of zinc oxide, that's the same as 1 mole. So I can just take these guys, and instead of saying 1 mole, just put my mass in. 97 over 81 is the same as 1 to 1. 1 mole of zinc sulfide is 97 grams. 1 mole of zinc oxide is 81 grams. Same ratio. It's just now all in terms of mass. Now our unknown ratio is even simpler. Because it's going to be X and 25 grams, isn't it? So let's put that in. All right, you see what happened? My goodness, I wasn't paying attention, was I? I hate it when equations look like this. X is in the denominator, I don't like that. I just feel much more comfortable if it's in the numerator, because I can cross multiply in my head, right? So, you know what I'm gonna do? Turn them upside down. Now wait, can I really do that? This is what I wrote because I wasn't thinking, I just wrote it. It's right. But mathematically, we could simply take the reciprocal of both sides, can't we? That's legal. So if you ever set these guys up, and it comes out upside down like this, just flip them both. Make sure you flip them both, that's all. Now it's so simple, it's obvious, isn't it? 25 times 81 divided by 97. We do our simple math here. And we get 20.9 grams of zinc oxide. All right, now this problem is designed to show you, two or three things. First of all, when we write an equation, this is going to be in terms of moles, right? And we can always write a mole ratio. But we can simply convert that to a mass ratio by sticking in the molar mass for the number of moles. So that's number one. Number two, if you set up these ratios and you happen to get them inverted so that you can't do it quickly on your calculator, that's why this X isn't up here, just flip them. Just flip them both, that's all. Legal mathematical operation. The last thing this problem is designed to show you is this word excess. When I say excess, that means we have all of the oxygen we need. So the amount of product we get is simply going to be based on how much zinc sulfide we have. Okay? So that's what excess means. Let's go ahead and look at this simple reaction. We're looking for how many grams of water reacted if we got 62.4 grams of HF. Now this was actually an exam question. So think about it. If this was on an exam, what would you do? We're looking for the relationship between water and HF. Two waters, four HFs, right? So what we would do is we would look at our stoichiometry. Say we have 2 moles of water, 4 moles of HF. And we want to do this in terms of mass. Two moles of water, 4 moles of HF. To express this in terms of mass, what do we have to do? we have to say that every mole of water weighs how much? 18. And every mole of HF weighs 20. So I could say 2 moles and 4 moles if I simply multiply it by the molar masses. That will give me a ratio of masses. This is the same as my stoichiometry, isn't it? So 2 moles of water at 18 grams each, about 36 grams. And 4 moles of HF at 20 grams each, about 80 grams. That is our mole ratio. Everything cancels except the grams, 36 to 80. This, we've seen this before, this is a simple mass ratio. All right, now we can address our question here. We have 62.4 grams of HF. We want to know how many grams of oxygen. So that's going to be X. X grams of water, I'm sorry, I said oxygen, I meant water. X grams of water, 62 grams of HF. That's from our problem. And our mass ratio here, this is the same as 2 moles to 4 moles, water to HF. And when we set this up and do it, again, by doing it, by leaving it as ratios, to me anyway, on the calculator is just so much easier, but so much less prone to mistakes. 62.4 times 36 divided by 80, 28.1 grams of water. Any questions? All right, let's look at this problem. Aluminum plus sulfur giving us aluminum sulfide. Balanced equation, everything is good. Remember when we did that problem before this last one? We said we had excess this or excess that, right? Read this problem. Here, we have 5 moles of sulfur and 11.2 moles of aluminum. Now, gee, what in the world are we going to do here? We need to know how many moles of product we're going to make. If I simply told you that we had 11 moles of aluminum and excess sulfur, all the sulfur you wanted, it would be simple, wouldn't it? You set up a mole ratio 2 to 1. You would do your unknown X to 11 and solve. Right? That's what you would do. But we don't have excess sulfur. We don't know that anyway. What we have to do here is to simply solve this problem twice. So let's think about our logic here. 2 moles of aluminum, 1 mole of product. 3 moles of sulfur, 1 mole of product. We're going to solve this twice with traditional way. We're going to solve it, see how much product we would get from 11 moles of aluminum. Then we're going to solve it again to see how much product we would get from 5 moles of sulfur. So, let's do that. 2 moles of aluminum, 1 mole of aluminum sulfide, right? Simple stoichiometric ratio. We have 11 moles of aluminum. We want to know how much aluminum sulfide. Oh shoot, I did it again. There, that's better. Once again, if you set them up upside down, so that you don't have to change this. You could completely cross multiply. That'll work. It's just psychologically, it's so much better for me if X is on top. So now it is. So all I have to do is take 11.2 times 1 divided by 2. I have 5.6 moles of product. So this is just like all the other problems we've done, right? It's a simple one. The only difference here is that now you need to take and write this number down somewhere. Write it on the back of your hand or something. I'll put it up there. Our 11 moles of aluminum gave us 5.6 moles of product, right? So let's go and do this all over again for sulfur. Step 1, write your mole ratio. 3 sulfurs for every aluminum sulfide. How much aluminum sulfide for 5 moles of sulfur? That's our question. Five times 1 divided by 3. 1.7 moles of product. All right, now it's time to think about the logic. How much product can we make here? If we react 11 moles and 5 moles, how much product can we possibly make? Could we make 5.6 moles of product? No. Why? Not enough sulfur. There's only enough sulfur to make 1.7 moles of product. There's not enough sulfur, is there? So we can't make 5 moles. We can only make 1.7 moles. This gives us 1.7 moles. This would give us 5.6 moles. There's not enough sulfur to make more than 1.7. Therefore, after we make 1.7 moles, the reaction stops because all the sulfur is used up, right? So how much stuff can you make? 1.7 moles of product. This is the concept of limiting reactants. In a limiting reactant problem, you're given quantities for 2 or 3 different reactants, okay? You don't know if it's exact. You don't know if one is in excess or not, which one would be in excess. You don't know that. So you have to solve the problem twice. Called a real pain in the butt, okay? Because you got to do everything twice. When you finally figure it out, when you finally figure out which one is going to give the smallest yield of product, that one is called the limiting reactant. The one that would make more product, if it only could, is the excess reactant. And the one we just did, sulfur, is limiting because there's only enough sulfur to make 1.7. There was enough aluminum to make 5.6, but it is in excess. Now, it is the end of winter, right? And if you have children, you might just be like rounding up gloves and sticking them in a box somewhere and saying, okay, how do we do over this winter? Well, in my box, I have 4 left-handeds and I only have 3 right-handed gloves. How many pair can I make? I can make 3 pair and I have 1 left over. That's the whole concept of limiting reactants. I only have enough right-handed gloves to make 3 pairs. So they're limiting. And I have excess left-handed gloves. This is not a difficult concept, but it is a bit of a bother because you have to do the calculations twice and then think about it a little bit. Let's think about this. You can take fluorine and react it with chlorine and make chlorine trifluoride. Now, why would you want to do this? Well, you would want to do this if you were enriching uranium to make bombs or whatever. Because you didn't react chlorine trifluoride with uranium hexafluoride, or make uranium hexafluoride, and that's what you use in your centrifuge. Okay, so this is a real sort of substance. Takes 3 fluorines for every 2 chlorines to make this stuff. Nice simple balance equation. Everyone happy with it? What if I tell you that we have 1, 2, 3 chlorines, and we have 1, 2, 3, 4, 5, 6 fluorines? How many chlorine trifluorides can we make? Which of these is in excess and which is limiting? Now you see, instead of having to calculate anything, all you have to do is play mind games, right? We have 6 atoms of chlorine, right? 3 Cl2s. Every chlorine requires 3 fluorines, right? So if we have 6 chlorines, we need 18 fluorines. How many fluorines do we have? 2, 4, 6, 8, 10, 12. Therefore, we can only make 4 chlorine trifluorides. We have 1 chlorine left over. Fluorine is limiting because there's not enough fluorine to react with all the chlorines, is there? Chlorine is in excess because we only need 4 atoms of chlorine to react with our 12 fluorines. Now, I said that you probably won't have big time calculations like this on an exam. Why? Why would I be nice and do that at this point in life? Why would I be nice and do that? Because you have to do all the calculations twice, don't you? So what do? Give you 2.5 times credit? Nah. So, the types of questions you can expect would be conceptual questions. For example, this is directly off last year's exam at Al₂S. Fluorine plus chlorine to give chlorine trifluoride. 9 moles of fluorine, 3 moles of chlorine. I'm not going to say, think about a concept. Do this in your head. 1 mole of chlorine requires how many moles of fluorine? 3. If we have 3 moles of chlorine in our mixture, how much fluorine do we need? 3 times 3 is 9. So, there's not excess chlorine. There's not excess fluorine. Fluorine isn't limiting. At the end of the reaction, everything has been consumed. Three moles of chlorine require 9 moles of fluorine. 1 requires 3, 3 requires 9. All right, we're going to take a quick break, and then we're going to look at limiting reactants in a simpler way. So not real simple, but a simpler way that will allow us to do it in 1 step instead of 2. Well, let's go ahead and take a quick break, and then we'll come back and pick that up. Yeah,
Is lead 5 on blackboard?
I'm sorry?
Is lead 5 on blackboard?
No, I had it back. I will do my best to get it up.
Just make sure that we don't big.
We had a good friend, Al. Just not a good. Got her home from the hospital yesterday. Right. I hope you had better. Good. All right, let's go ahead and pick this up again. Let's just look at what we've done the first hour, do a couple quick review problems, and then we'll move on to mass ratios and a shortcut way to do limiting reactant problems. Again, we talked about simple stoichiometry for our aluminum-bromine reaction. We know that 2 moles of aluminum, 3 moles of bromine gives us 2 moles of aluminum bromide. What we did was we set up a mole ratio. The mole ratio simply describes a problem here. If we want to know how many moles of bromine to give so many moles of aluminum bromide, we look at our equation, set up a known mole ratio. We can then calculate an unknown. The calculation that you do gives us a number of moles or a number of grams or something. That is the theoretical yield for the reaction. That means if everything is perfect on earth and heaven, that's how much stuff you should get. If we had exactly 2 moles of aluminum and exactly 3 moles of bromine, theoretically we should get 2 moles of this stuff. That's what we mean by theoretical yield. It's simply based on the stoichiometry. If we take chloroacetic acid, react it with oxygen, we can get carbon monoxide, water, and HCl. We make 0.2645 moles of carbon monoxide. How many moles of oxygen did we use? Step 1. We're looking for a relationship between carbon monoxide and oxygen, right? 1 mole of oxygen, 4 moles of CO. Step 2, we set up a known ratio. 1 O2 to 4 COs. What is our problem? What's the question? How much oxygen? That's X. 0.26 moles of carbon monoxide. And so we write this. And how do we solve this problem? 0.26 times 1 divided by 4. 0.066125 moles of oxygen. We have 4 significant figures. We're going to round this even. This is a case where we round it down to make it even. So this is a simple calculation where we just get moles, correct? Any questions at all on how you figure this through? We can do the same thing in terms of mass. Here we have boric acid. We warm it up, we can form a borate anhydride and kick out water. We want to know how much of this anhydride we're going to make if we have 36 grams of boric acid. So what do? Looking for a relationship between boric acid and borate anhydride, right? It's 6 to 1. Get to set up our ratios, our known and our unknown, but we want to do it in terms of mass. So we always start out with a mole ratio. 1 anhydride for every 6 boric acids, right? Now to make this into mass, we know that every mole of this anhydride is going to weigh 244 grams, right? And we know that 1 mole of boric acid is going to weigh 61 grams, 61.8. Therefore, if we multiply this out, we're going to get, for every 244 grams of anhydride, we need 371 grams of boric acid. That is our simple mass ratio. Mole ratio times molar masses gives us our mass ratio. Now we can just take this and plug it into our standard equation. We want to know for every 36 grams of boric acid, how much anhydride will we get? Anhydride is X. Our boric acid is 36.3 grams. So once you set it up, 36.3 times 244 divided by 371 gives you about 24 grams of anhydride. So we solve these problems 2 ways, using simple mole ratios and using simple mass ratios. Any questions on either one of these guys? We talked about the concept of limiting reactants. Remember the way we did it? We did it twice. Whichever one gave us the smallest amount of product was limiting, because that's all product you can make. That limits how much you can make. Only make 3 pairs of gloves. The other stuff, therefore, must be in excess. We looked at this problem once again. Every mole of fluorine requires 3 moles of fluorine. If we had 3 moles of chlorine and only 6 moles of fluorine, we can only make 4 moles of product, and we have chlorine left over. Think about it in terms of gloves. You have 2 kids and every kid needs 3 gloves? Not quite, but. All right, we looked at a problem last time from last year's exam at UIC. This one was from the year before. Three moles of fluorine, 3 moles of chlorine. What's the right answer? Come on, it's just a cartoon. You guys can do cartoons.
No, it's not.
All reactants
That was on the last one.
No,
Don't do what you did on the exam.
I think fluorine is the excess. Fluorine is the excess.
Every mole of chlorine requires 3 moles of fluorine, right? If we have 3 moles of chlorine, how many moles of fluorine do we need? 9. How many do we have? 3. Is that enough? No. No, it's not enough.
So it's limited.
Therefore, there has to be more chlorine than we need, and fluorine is limited. You know, on this exam that you took, you two, the one we did in class, the first problem was sodium hydrogen sulfate, or ammonium hydrogen sulfate, right? And the answer to that was B. On the actual exam, that was changed to sodium hydrogen sulfite, but the name was still written as sulfate, so that was wrong. A, however, was changed, so it was now correct. So, and everybody missed it. Everybody put B. Everybody. All right, we just did this problem. We said we had 5 moles of sulfur, 11 moles of aluminum. We want to know how much product we're going to get. We did this by setting up our ratios, right? First thing we did was calculate that we needed, or that our 5 moles of sulfur would give us 1.7 moles of product. We also calculated that we had enough aluminum to make 5.6 moles of product. But we don't have enough sulfur to make 5.6 moles, do we? Therefore, this guy is limiting, and this is in excess. We can only make 1.7 moles of product. That's the concept of a limiting reaction. So let's go ahead and, just for the heck of it, do one of these in terms of mass. And we're going to do it the same way. We're going to set up mole ratios, convert those to mass ratios, solve to see how much mass we could get from 10 grams of aluminum oxide and from 2 grams of carbon. 2 separate problems. Whichever one gives us the smallest yield wins. That's limiting. So all of this is flashed through your head. One mole of aluminum oxide gives us 2 moles of aluminum. 1 to 4, 1 to 2, 2 to 4, doesn't matter. 3 moles of carbon, 4 moles of aluminum. We want to do this in terms of mass ratios, not simply mole ratios. Aluminum weighs 26.98. Aluminum oxide, 101.9. Therefore, if we have 2 moles of aluminum, that's the same as having 2 times 26.98 grams of aluminum. If we have 1 mole of aluminum oxide, that's the same as 101.9 grams of aluminum oxide. Multiply this out, our ratio is about 54 to 102. Now, Everybody here can do that. I have no doubt. Our problem here, we have 10 grams of aluminum oxide, and we want to know how many grams of aluminum we're going to get. X grams of aluminum for 10 grams of aluminum oxide. All we have to do is 10 times 54 divided by 102. See how I can round those in my head? .29 grams of aluminum. So our 10 grams of aluminum oxide is enough to give us 5.29 grams of product. That's what we've just calculated. And so we write it down. Now we're going to do it all over again for carbon. 3 carbons, 4 aluminums. Carbon is 12. Aluminum is 26.98. So 4 moles of aluminum is 4 times 27. 3 moles of carbon is 3 times 12. We cancel things. You would get 108 grams of aluminum, roughly, for every 36 grams of carbon. Now we are given that we have 2 grams of carbon, right? So set up your 2 ratios. X moles of aluminum, 2 grams of carbon. 107.9 grams of aluminum, 36 grams of carbon. Two times 107.9 divided by 36. 5.99 grams of product. Now, we have enough aluminum oxide to make 5.29 grams of product, right? We have enough carbon to make 5.99 grams of product. All you have to do is say which one of these is smaller, right? We only have enough aluminum oxide to make 5.29 grams. Yeah.
I have a question. What if you were to deal with the carbon dioxide as opposed to the aluminum?
Well, it would be a different problem, but the end result would still be the same in terms of the fact that aluminum oxide would be limiting.
So it doesn't matter which one you choose to deal with?
No, that's whichever one the problem is stated for, that's all.
Because it doesn't say anything about just aluminum. Plus there's no carbons in the aluminum.
Which reactants it
You know what I
Oh,
mean?
you're right, okay, you're right, I didn't put that in the problem, I didn't realize that. So no, we could have solved it for aluminum or CO2, either one.
Okay.
I probably meant to put aluminum in, sorry. So, aluminum oxide is limiting, carbon is in excess. So this is what we've done before, except we did it in terms of mass. And we had to do everything twice, and then we had to think. Right? What if, instead of doing everything twice and then thinking, we could just do this once and think? That would be better. Therefore, I'm going to ask the question and say, how much aluminum oxide do we need to react with 2 grams of carbon? Now, I could have asked it the other way around. I could have said, how much carbon do we need to react with 10 grams of aluminum oxide? Either one. But I'm just going to ask the question. If we have 2 grams of carbon, how much aluminum oxide would we need? Does everyone see how we did this? If we had 2 grams of carbon, how much of this stuff would we need? All right, so let's solve it. Aluminum oxide, 101.9, carbon is 12, right? Our ratio here, 3 carbons for every 2 aluminum oxides. So we're going to set up our mole ratio. For every 3 carbons, you get, or you need 2 aluminum oxides. Correct? Now, every aluminum oxide weighs 101. Every carbon weighs 12. Therefore, we can write a mass ratio. Cancel. Every 36 grams of carbon gives us about 204 grams of aluminum oxide, or requires about that. This is just like everything we've done so far, right? Just like what we've done. Now we have 2 grams of carbon. How much aluminum oxide do we need? Every 2 grams of carbon, how much aluminum oxide? 2 times 203 divided by 36, 11.32 grams of aluminum oxide. Now think about what we just did. If we had used up all of our carbon, if we used it all up, how much aluminum oxide will we need? 11.3 grams, right? If we used up all the carbon. But how much aluminum oxide do we have? 10 grams. Not 11.3. We don't have enough, do we? So with this one calculation, you have figured out that we don't have enough aluminum oxide to react with all this carbon. Therefore, aluminum oxide is limiting. We would need 11.3 grams, we only have 10. Therefore, this must be limiting. Now, isn't that simpler? It's not simple, but it's simpler. If we had 10 grams of aluminum oxide, how much product would we make? This is a simple stoichiometry problem, isn't it? This is one of the simple ones. We would set up our mole ratio. We're talking aluminum and aluminum oxide. We only have 10 grams of this. Our mole ratio is 2 to 1. Our mass ratio, we multiply these by molar masses. Here's our mass ratio. We have 10 grams as our given. These cancel. 5.29 grams. Same thing we got the other way. But again, we didn't have to do this calculation, did we? Because we were able to stop when we said Needed 11 grams, we only had 10. Doesn't matter which one you choose to work. They both will turn out exactly the same. Let's do one more here. There's our friend, ethane reacting with oxygen to give CO2 and water. We have 22 grams of ethane, 16 grams of oxygen. How much CO2 will we get? What if we changed it and said, what mass of ethane do we need to react with 16 grams of oxygen? So we don't have to do everything twice. We're given that we have 16 grams of oxygen, 22 grams of ethane. If we just simply used up all of our oxygen, how much ethane would we need? Every 7 moles of oxygen requires 2 ethanes. Ethane weighs in at 30, oxygen at 32. Ooh, there's a mistake on the slide. That should be 32, but let's leave it at 16 because I think I did all my calculations that way. So if oxygen really weighs 16 grams per mole, this is our mass ratio. Now, we have 16 grams of oxygen. There's our mass ratio, even though it's wrong. It should be twice as large. Simply solve 16 times 60 divided by this, and that would be 8.59 grams of ethane. How much ethane do we have? 22 grams, right? That's more than enough. That's more than enough. Therefore, the yield in this reaction is simply based on oxygen. Now, because I made a mistake in the slide here, I'm not going to go ahead and finish the problem and calculate a mass, because it'll be wrong. But everyone understands that. At this point, we would simply, if we want to know, if we want to know the mass of CO2, we would simply take our 16 grams of oxygen and do a simple stoichiometry problem. Now, on an exam, I would not ask you a compound problem like this for 2 reasons. First of all, it wouldn't be fair because you'd have to do lots of calculations, have to think, then you'd have to do another set of calculations, and if you made a mistake early on, then it wipes out the whole problem, doesn't it? So I wouldn't do that. On the exams, you can probably count mostly on simple conceptual questions. So something like our little cartoon with chlorine and fluorine, etc. Those types of conceptual questions. Any questions? All right, let's go ahead and quit.